Our guest presenter today is called Shahzeb Hassan Muhammad Ismail. He has a bachelor's and a master's of engineering in chemical engineering, and is a chartered chemical engineer with the UK Institution of Chemical Engineers, ICHEMI. I'm going to implore all of us to go and search about ICHEMI, Institution of Chemical Engineers, UK. It's an institution that regulates the work of chemical engineers in the UK. It has a global outlook of chemical engineers. You can consider joining that institution. He is a chartered engineer with the UK Engineering Council, and he's a professional engineer in Pakistan and a registered engineer in Saudi Arabia. He has extensive experience in oil and gas and the petrochemical industry. He has commissioned multiple refinery projects, and as such, he possesses proficiency in process engineering software. Among the software that he has expertise in include Aspen Hysys, Aspen Plus, Unisym Design, Aviva Pro 2. I saw some of you were struggling to download and install Aviva Pro 2. Shahzeb has experience in that. I hope he will share his experience and maybe advise or guide on how you can install one. He has numerous experiences in other softwares like hydraulics, process historian, KG Tower, SAP, to mention but a few. He was selected as a finalist for the Global Young Industrialist Award 2021 by ICHEMI. This is an award, an annual award by ICHEMI. So in 2021, Shahzeb was selected as a finalist. And one of his stories as a process engineer was published on the AICHE platform, that is American Institute of Chemical Engineers. It's also a global body of chemical engineers in America, USA. His work as a chartered chemical engineer was featured in a case study by the Engineering Council UK. Personally, I have read this. You can visit the UK website, Engineering Council. In Uganda, we have the Engineering Registration Board. The equivalent in UK is the Engineering Council, the board that regulates the engineering profession in UK. So his work as a chartered chemical engineer was used as a case study by the Engineering Council, UK. He is a technical writer for the International Association of Certified Practicing Engineers, quarterly magazine. He is an initial professional development assessor for ICHEMI. What I want to let you know is Shahzeb is actually my mentor for the ICHEMI. I'm in the process of registration with ICHEMI, and he's actually my mentor. There are stages that you go through. There are like 3 stages for you to become a full member, a chartered chemical engineer with ICHEMI. The first stage is ICP, individual case procedure, where they verify, they assess your education background. And then the second one is the IPD, the initial professional development. Here they assess your experience as a chemical engineer. So he is an initial professional development assessor for ICHEMI. He assesses professional experience for those who want to become chartered engineers. Shahzeb has also supervised many undergraduate chemical engineering final year projects as an external supervisor for several universities. This is an opportunity to bring to your face a global expert in the profession that you are in. Take this opportunity as serious. You can connect with Shahzeb on LinkedIn using those names I've put there. He will do welcoming to connect with you. Feel free to engage with him and learn. So the purpose of this session is basically to engage and listen, understand, and ask a few questions on what process modeling, and simulation of chemical processes. This is an opportunity that comes once in a while. So for Shahzeb, on the call we have graduates of chemical engineering from Uganda. They are young engineers, very eager to learn from your experience and expertise. I want to take this opportunity to invite you and speak to the young engineers of Uganda and the globe at large. Maybe you will have to share your screen, the video, a little for them to see you, and then you can share your presentation. Over to you, Shahzeb. Thank you. I'm going to stop sharing.
Hello, everyone. Yes, my voice is clear.
Yes, your voice is clear.
Yes, Mr. Benard, thank you very much for introducing me. I'm very thankful to you for giving me this opportunity to explain the young minds regarding the power of process simulation. Uh, as per my experience, since 2014, I started my career, and during my initial training, I was really interested at that time to learn about the process simulation and modeling. So I started doing it at that time, and it's been now 11 years since I've been using all these softwares. And this softwares actually help me to perform the troubleshooting, process optimization, process image process simulation, and cost savings. Um, And as per me, sorry, I'm not showing my camera because I think internet connection is not good. It is hanging. So, so where I'm saying that process simulation and troubleshooting is one of the major skills required in the industries nowadays. If you want to work overseas, you need some kind of extra skills to show to your employer that you can save money for them because anybody hire you uh, to work because they want to save money and earn money. Save money in terms of optimization and earn money in terms of profit. So the idea you put on the table in terms of the management of any industry, uh, always looking after with few reasons that one of the reason is the cost optimization. Because if you want to work as a process engineer job is you can say it's a mind of the industry. Without process engineering, industry would not survive because process engineer deals with the operations that ask the operation to do things which require um, the steps that they don't know. For example, operation running the plant at high steam load, and you know that from your this is just one example. You develop the whole model in the process simulation, and identify that even at the lower stream you can survive. So why you are adding more stream? So more stream means if you see the impact in dollar per hour, it will be higher. So you will ask operations team to justify that why they have increased the high stream in the column as there was no need. So at that time, the process engineering role comes in. Process engineering, you tell them that you need to reduce the steam and optimize the column in such a way, the column reflexes, overhead reflexes, column temperatures, straight temperatures, that you don't need such high steam and it will save this one amount of money, this much amount of money. So process engineering role with the process simulation is very important. And in the future, if you want to work like process safety engineer, then you need process engineering background. If you want to work process control engineer, you need to have a process engineering background. And with the process engineering, you can move in any other field. Like you can work in operations as well. You can work in process safety, process control, even safety. Because all the work process engineering do, um, they must comply with the safety, like MOCs, management of changes. If I'm suggesting anything that will save money and that will require maintenance support, then I will raise MOC, management of change. That will go to the approval process of all the team members, the OME, we can say, operations, maintenance, and engineering support. They will approve it and then it will go towards the implementation. You know, for example, you have the column upset, your plant is shut down. Then the operations team will raise the TTR, trouble and trip report. Then it will come to the process engineer. Process engineer will do the evaluation first and it will be forwarded to the next department if it is required. Otherwise, process will lead most of the investigations because process engineering is an eye and brain of the and the coordination job of process engineering is also very important because it coordinates with operations, process control, laboratory, everything. So today, if I share my screen, so my screen is visible.
Yes, yes, I can see it. Some other person can confirm if they can see your screen. Can someone confirm if you're able to see the Word document?
Yes, but it's
Yeah, I can see.
unclear.
I can see.
Yes, increase this. Yes, I think that's better.
Yeah, yeah, that's
Okay.
perfect.
Yes, yes.
Okay.
So because I have worked on different softwares like Aspen Hysys, Aspen Plus, as Mr. Benard introduced me, and I took the training of Unisim design in Dubai office. And I also know the Viva Pro 2 softwares because previously I was working with the management team to develop the training videos for them. And I also have the YouTube channel, uh, Smart Process Engineering. You can join there also because every day I think that if there is any gap between industry and university, I develop one video of any new softwares to introduce them into the market and download and upload it into the YouTube channel. Although it is not much active now because recently last year I moved here in Kingdom from Pakistan. So my job role is also changed. Previously I was working in the petrochemical industry, looking after the ADC plant, but now I moved to the refinery again. I started with the refinery, but then I moved to petrochemical. So in my current role, I'm looking after the CDUVD unit, the distillation unit. And in my previous role, I was looking after hydrotreating and reforming unit. So to simplify this workshop, and as I know that maybe some of you have no background of using the softwares called Aspen Hysys, which is an Aspen tech product. So starting with the Hysys, I developed this document to introduce the software to you. And during the workshop, we will go through this case. Let me start explaining the case. We have one stream containing 15% of ethane. Ethane is a hydrocarbon. Second chain, 20% of propane, 60% of isobutane, and at a specified temperature and pressure. So the flow rate we set for the stream is 100 pound more per hour, and this stream is required to be compressed. So we will add a compressor. First we will add a stream, and then we will add a compressor, and then we will add a cooler to reduce the temperature, because during the compression the temperature of the stream will be increased. The resulting vapor and liquid we will separate through a separator, and from the top of the separator we will get the vapor, and from the bottom we will have a liquid. And these are the conditions which we need to comply with the software. So we will go through this with the help of softwares. So I put the worksheet and the software on one screen. So it is now visible to all of you, both, or should I change it to a single window?
To me, it is visible. Maybe some other members here can propose. Are you guys okay with one? Okay.
Okay, this is the initial window of the software. When you open the this icon called S1 Assist, uh, this kind of window will open. So here you can see in the resources, they have embedded some features like what's new, examples, training module. But some of these modules in the offline mode is inactive. They will only be working when you connect uh, with the Aspen Tech team. Otherwise, you can work on it. Like for examples, you click it and you have different examples, which was developed by Aspen Tech team itself for reference purposes. So you can open it, and if you have a similar kind of a problem, you can click on it, and uh, you can put your own data into the simulation and get the results. And what's new? You can any feature you want to explore that. For example, if I want to see the fluid package, if I write here, it will show me about fluid packages. So all the information or regarding the fluid packages you will find here. Adding the fluid packages, copying the fluid packages. So it's kind of library for the software. So anything you don't understand, you can take a reference from it. So starting with the new, if I click the new, it will open this kind of window. So the first step in the process simulation that you need to add the components, means the components involved in your process. So in my problem, or in my case, the component is ethane, propane, butane, and normal butane. These are the four components I see in the problem. So in order to reflect it into the simulation, we need to add the components like this. So introducing our top window, you can see this is the normal options, cut, copy, paste, component list. You can also get from here, component list. We will see later on. Root packages, there is an also option. So either you can click from here or either click from here. It's up to you. Method assistant and reactions profiles. This can also be opened from the options given on the left hand side. So I usually use this one because it is showing an indication. That means they need the value, they need some inputs, and blue means it is satisfied. So coming to the petroleum assay, and if you have to study the petroleum assay, means crude assay, the characteristic of the crude. In the Aspen Tech library, you have around 500 already embedded crude assays. Uh, for example, any crude which is using and which is currently uh, can say processing in Uganda, you can see in the library that I will show you this option in the at the end of the workshop. Okay, because I if I will open it, then the mode of this window will be changed. So, for example, any food which is being processing in the Uganda, you can see that if it is available here or not. So, more or less, the properties are the same. The other option is that you can add your food as if you have the lab quality QC, you can add it. And because if you want to perform the distillation of the crude assay, then you need an oil manager or petroleum assay.
Shahzeb,
Yes,
that can you increase the size a bit?
reduce, increase.
Increase.
Actually, this window, I don't know. This could not be increased, I think. This is standard window.
That yes. That's a standard size, you guys.
This is the laboratory measurements, the last one, and you need to connect the data from the laboratory. But we are doing this offline, so we could not connect it. So to make it more simple, let's start with the component list. If we click add, now the component list is showing here, the library. Okay, so these are all the hydrocarbons and polar non-polar compounds all in the library. If any component you don't find here, then you can create a hypothetical. Hypothetical is based on molecular weight. You must have the molecular weight and the final volume point to create the hypothetical. So because this is the first workshop, and if I dig in every option, then it will be very complicated for all of you to understand that what is happening. So let's start with the workshop to develop an understanding on the software. So considering the components we have, first one is the ethane. So when I click ethane and add, it will be added in the system. And you see, because one component is added, this status changed to blue from red. But now we have propane and isobutane. Propane I will add, and I have also isobutane and normal variant. So we have a stream running these components. Okay. The second step, first you have added the components. Now the second step to add a thermodynamic package. So you guys are following me? Is it okay? You understand what I'm saying? What I'm explaining?
Are you guys understanding what Shahzeb is explaining? Do you understand his
If you have,
accent?
Yes, we are following.
We can understand.
if you have any question so far, then you can ask. And if you have any question, you can also ask during the workshop. During I'm explaining, you can just stop me and ask the question, then I will reply. Then it will be an interactive section. So coming to the fluid package, I will add, and we have thermodynamic package, different package. But here you have to choose that which package is suitable for your components because we have added hydrocarbons. Ethane is a hydrocarbon, propane hydrocarbon, and these are isomers, but still hydrocarbon. So this selection of packages, first based on the experience, means any process simulator who have more experience who learned during the exercises that which loop package is the best for the components. So they don't need any guideline to follow. So I will select the Bang Robinson, which is comply if we have pressure less than 100 bar. But I have downloaded it um, one guideline, this one, for the selection of the packages. So here, this is the tree of selecting the fluid packages. If you see here, all gases are non-polar. You can try Bang Robinson, SRK, API. It will work. Maybe uh, some of the results from different packages are different, but more or less the estimated one are the same. If you have electrolytes, then you can try an RTL, Pitzer, Bromley, and binary interaction parameters. If you have gases that have a pressure greater than 10 bar or ammonia CO2, you can use this. So uh, for the starting of learning the software, you need to have this pocket dictionary with you to understand that what are your components and what fluid package will be comply with your simulation to get the correct results. So considering the pressure less than 10 bars, you can uh, select the handles now. So all these fluid packages are available in the software. You just need to click on it and that will be selected and showing you the status okay. So these are the two major steps in the beginning of starting the simulation. That these steps are the important one because if you don't select the correct components and the fluid packages, then all the simulations you will do later on will not give you the correct results as you are expecting. So this initial steps are the key to have a successful process simulation model. The first one is the component list. You will add the components which are engaged in your process, either hydrocarbon or non-hydrocarbon. The second one is the fluid packages. Fluid package is a thermodynamic model. The thermodynamic equations which you study during your undergraduate, like Bang Robinson, this is PV is equal to nRT minus small a upon B. So different kind of equations that will trigger the thermodynamically give you the results. So now here we are in the properties phase. You see in the simulation. So in order to go to the simulation phase, you need to click here, simulation, because this is Aspen Hysys. If you see other softwares like Unisim Design and Aspen Plus, they have different uh, mode of operation to go into the simulation environment. So if I click in the simulation, then the model palette of adding the equipments and streams is open and my flow sheet. This is a blank white flow sheet for me to start the simulation. So starting the simulation, I have to add some streams because at the plant we have pipelines. You see, for example, if I take the example of crude refinery, you need to have a pipeline from the tank, then it goes to the pump, then the pump increase the pressure of the crude oil, then it goes to the preheat, increase the temperature, then that salting will carry out to remove the salts and basic sediment water. Then a second preheat, then it goes to furnace and get the required temperature. Then it will flash in the distillation column. In this distillation column, it will be separated based on the boiling point and relative validity. So, considering our process, I will start with blue stream. This blue color means material stream, and this red color means energy stream. For example, if you have large number of sheets, then you can develop a sub flow sheets. Means this flow sheet, there is another flow sheet showing like this, and when you click it, it will go and open another flow sheet. So considering my stream here, I put just click it and paste it. Double click, it will paste like this arrow, and just delete all and add another one. So If I double click it, it will open like this window. The first window is the process parameters, pressure, temperature, flow. Blue is showing the input, but you don't need to add all the inputs. You just need temperature, pressure, and phase change and flow. Either you can put phase flow or pressure, phase flow or temperature, it's up to you, or you can add temperature, pressure, and flow. So in any case, you need three parameters to convert your simulation and the composition. So on this left side window, you have properties, composition. So starting first, uh, when we start the simulation, first we add the components, then the fluid package, then we go into the simulation environment. The simulation environment, we learn about adding blue stream or red stream. Blue is the material stream because now we are doing the material balance to get the results. And red is the energy stream. Energy stream will be connected with the coolers like heaters, the boilers. This is the energy stream. The output of this stream is energy, kilojoule per hour, BTU per hour, like this. So starting with the composition palette, when we click edit, it will open another window, and here we need to add the required amount which we have. For example, we have 15% ethane. So here we are adding in mole fraction. Mole fraction means 15% divided by 100. How much it is? 0.15. Propane 20%, 0.2. Isobutane 60%. This total should be 1 because we select mole fraction. So only 5% is remaining, and in the question, even in the problem, it is showing 5% and butane is remaining. So you can write here like this one. It is now showing 1. It is satisfied. For example, you don't know about the composition of the fourth one, empty. So when you click normalize, it will put 0. And it will also adjust your other compositions to make this at 1. And because we have the composition, so we don't need to put the normalize. And this is a composition control that we need to erase all and equalize composition like 0.2, all 1. But 1 could not be accepted because it is more than 1. So if you have mass fractions, then you can click mass. If you have flows, then you can click flows. These are different options to add. We have more fractions, we will add another like this 0.15, 0.20, 0.60, and 0.05. So we have added up to 1. When we click OK, it will show here. So if we want to change the basis later on that we have already added the composition in the mole fraction, but we want to see this composition in mass flows. Here it will not show as mass flows because we have not added the mass flow. So we will see this option later on. Now we have added the composition, and now it is showing a triggering a message that unknown temperature. This ISIS is a user friendly, more user friendly than Unisim and Pro2. So you just need to add, follow the steps the software gives you. Here it is showing unknown temperature. So I will go to the condition also, and here is the temperature. So the temperature is 50 degree Fahrenheit. So here it is showing in centigrade, and I have 50 degree Fahrenheit. So I have two options. Either just click 50 and change here into degree Fahrenheit. So now it is changed to degree Fahrenheit, but it is showing me in degree centigrade. 10 degree centigrade is equal to 50 degree Fahrenheit. It is also showing like this. This is the first option. if you want to set the unit system of unit inside it. If you want to change the system of unit, then you need to click here, unit sets. This window will open, and here you will find temperature with the T here. We will change it to degree Fahrenheit and click OK. It changed to degree Fahrenheit. Now it is showing 50. So the pressure we have is now it is showing unknown pressure, atmospheric pressure. So atmospheric pressure 1 atm. I will click 1. I will open and see pressure units 1 atmosphere.
Shazeb,
Yes,
I request that we maintain SI units.
SI units.
Yes.
Okay. For the SI units, if you want all the units in SI, then you have the option available here, available unit sets. Here it is showing SI. When you click it SI, you click OK, all the units change to SI. Change KPA like this. So because in the problem it is showing 1 atmospheric pressure, so I will change 1 when I click. You see here G is showing with the atmospheric G, it means gauge pressure. But we need atmospheric pressure, we will click 18. So as we know, when we convert the unit, 1 atmospheric is equal to how much kilopascal? 101.3. So now in the SI units, we have degree centigrade, kilopascal, joules in kg per hour, and meter cube per hour. So next we need to add, here it is showing unknown flow rate. So what flow rate we have? 100 pound mole per hour. So we need to convert 100 pound mole per hour in kg kilogram mole per hour. So when I click 100, I will change the unit to pound mole per hour. Pound mole per hour. Okay. So it will convert automatically into SI unit and show me the value in kilogram mole per hour. But in actual it is pound mole per hour. See, and it is also when I move the cursor on it, it is showing also 100 pound mole per hour is 45.36 kilogram mole per hour. And now the stream is converted, is showing okay. Now, if you want to see the properties, here you can see the molecular weight. Means on daily basis, if you are a process engineer and you have different kind of work, like if you being asked to give the data required for the designing of any control valve, then the designer asks you to give the molecular weight CP by CV. So all this data, if you don't have, then you can simulate the process and find out these values and hand over to the designer. These are all the properties. And if you want to see more properties, you can click plus. You have this available. If you want to see check portfolio, then you will click any and apply. It will be added in the last composition we have added. This is one oil and gas option. So we don't have an oil and gas, so we will not use it. Petroleum assay. If we do the petroleum assay in the starting, then we can attach it here, but we don't have, so this will remain as it is. So now the system is satisfied. It is showing okay. We will see here. So we can change its name here. Feed. Now the first step we have done, we have developed the feed plant feed, which contains 50% ethane, propane, butane, and normal butane. At a pressure of this and a pressure flow of 100 pound per mole. It is ready. So, when I right click on it, When I click show table, it will show me temperature, pressure, load. So the next step is to add the compressor to increase the pressure from to up to 50 psi. Okay, we have here equipments, different equipments. This one, if you just put the cursor on it, it will show you the name of the compressor. Oh, any equipment, tank, three-phase separator, expander, station column, pump, heat exchanger, cooler, like this. Dynamic controls want to see ratio controller, split range controller, heat transfer, all equipments, manipulators, all equipments, piping hydraulics. So this is the all you will get in one palette. And if you want to see specific like separators, you have all these. So this is the model palette. We have one compressor, so we will click it, compressor, put it here. It show us the compressor. Compressor. There is a workbook for this. When you click this workbook, it will show like this. Composition, we have added already. Energy, no. Compressor equipment, unit operation, compressor we have no. Now we have two options. Either we will click control and this will show like this. We will drag it and connect it with the compressor. So this is not the right point. We will add this and click this. Now disconnected. The previous point was for the screw wall compressors. If we have screw wall means liquid, then we will connect here. And for the product, we can click here, this point, and it will add a new stream for the product. We will add compressor discharge. There is another option. When you click it, this equipment, it will show you like this palette. Here you will write, for example, I add the feed here. So if I disconnect here, break connection. Now if I don't know that how to connect this stream here, I just click the compressor and see available feeds. It are automatically connected. And if I don't have stream on the palette and I want to add new stream, then I write, for example, energy stream is the energy stream. The compressor require energy to pressurize the feed stream. If I put the name of candidate, it will add. Previously it was showing red because the stream was not available. Now it is showing yellow because the compressor require process data to run. And even here it is showing unknown duty. It means you need to add the pressure. So you have two options. Either you can add here the data, for example, delta P spec. If I know, I will put here and it will start working. Or either I will click the stream here and what I will do, I will put only the discharge pressure and temperature will be automatically calculated. So we have the discharge pressure 2 psi. I will click 50 psi. Okay, so it converts. Temperature automatically calculated, all parameter automatically calculated. Compressor duty calculated based on discharge pressure and pressure ratio also calculated. So I have not input the delta P spec, but it is automatically calculated as 243.4 kilopascal. Just putting the discharge pressure of it, the unit is converged. The second option is that I don't put the discharge pressure, and I put here the delta P, 243. Again, it is converged. But now there is no option to change the input. Every time I have to change the compressor pressure, I need to change this delta P. Then I will get the discharge pressure. So normally we put the discharge pressure directly into the steam to get the duty from the compressor because during the case studies it will be easy for us to use the steam pressure rather than using the delta. But in actual, uh, for the compressor curves, they consider the differential pressure. So during the initial phase of simulation or the learning phase, you can select the discharge pressure as I suggest. And but when you become master of the simulation, you will know that where and how the parameters need to be put. So now one equipment is converged and this equipment showing okay, and we have the discharge temperature of 7.59. When I click show table, it will show me pressure, product pressure, molar flow like this. So the compressor model is developed. Now with this model, I can see the discharge temperature, the change in properties, for example, density, vapor phase, how much, and liquid phase, how much. And now if I see the workbook, material streams, it is now added two streams. So overall, if I want to see all the material streams, then I can work on this workbook. This blue color is showing the inputs. I can change it as I want. For example, if I change it to 12, it changes and gives me the result in the simulation. And if I change to 50, you can see the temperature is increasing to 98.5. Now, the next part of the simulation is to add the cooler. And I click this flow sheet modify, it will show me again model palette. And when I click this cooler, I will add cooler and connect the streams. Now I put cooler outlet. This is the energy stream. So the lower temperature I put here, automatically it will calculate that how much energy this equipment required to be removed to achieve this temperature. If I have the energy stream available, then I will put the value here, the energy to be removed, and it will give me the discharge temperature. So here we need to reduce the temperature to 32 degree Fahrenheit. So here I will put 32 degrees Fahrenheit, 0 degrees centigrade. When I click it here, it is showing me the parameter which I need to add, which is unknown delta P. So I will put that there is no pressure drop in the cooler. I will put 0. So it converts because this delta P data is not given in the push. Now it is converged. Now we have added the cooler E100. The last part of the simulation is to add a separator that will separate the liquid vapor. And here I have three-phase separator and two-phase separator. Three-phase separator means we have hydrocarbon liquid, hydrocarbon gas, and water. Three-phase. Here we have only hydrocarbon liquid and vapor because we cool down the stream of hydrocarbon. So here it is showing vapor fraction 0.233, 80% liquid and 20% vapor because we reduce the temperature to condense the hydrocarbon into liquid phase. So this fraction of 0.23 overall steam means in the vapor phase is 20% and in liquid phase it is at 80%, around 80% approximately. Now we need to separate this into liquid and vapor because now we have developed a two-phase stream, liquid vapor stream. We add a stream of hydrocarbon, we compressed it, increase the pressure, in increasing the pressure, increase the temperature. We reduce the temperature to condense the hydrocarbon into liquid and vapor phase. Now we want to separate into liquid and vapor phase through a separator. So the separator works on thermodynamics. We will click here, put separator here. We connect. This is top from the vapor stream, bottom liquid stream. We will put for vapor for V and liquid for L. Now if we see there is only one vapor, one zero means showing 100% vapor. And flow is 459 kg per hour. So if I click this vessel and go to the worksheet it will show here me the overall profile of the column. Liquid is 0. 0 means 100% liquid. 1 is vapor, which means 100% vapor. So in terms of kg per hour, my feed cooler outlet is 2300, in which liquid is 80% around, which is 1860, and vapor is 455. We separate liquid and vapor with the separator. And we can also see the properties of liquid and vapor like this because vapor molecular weight is less, liquid high, density change, liquid density for liquids are high and for gases it is low. So all these properties you can find from here. And if I click here, then it will show me the overall profile. So in this simulation, what we need to check, we need to see that at this temperature, how much is the vapor and how much is the liquid we generate. Hydrocarbon from ethane to isobutane and normal butane. So far, if you have any questions, please ask.
If you have questions, you can ask as we progress.
So this is the model we have developed because our objective was to see the liquid vapor ratio in the hydrocarbon, that how much liquid will generate if we reduce the temperature of the discharge stream to 0 degrees Celsius, 32 degree Fahrenheit. So if I click show table here, Now if I click here, now see, this is the temperature of the cooler outlet, this stream. Okay, I can change the icon also. Okay, now I will put 4. Now change in flows. See, if I put 4, more vapor now. See here, more vapor, less liquid. At 15 degrees centigrade, all vapor. 11, some vapor, 14, still vapor, 14.5, still liquid available, 14.8, 14.95, 14.92, 15.90. So 14.91 is the temperature at which we get all vapor, hydrocarbon, and that is our dew point, 14.90. 14.90, we have some liquid. 14.91, but as you see that I am manually changing this. There is another way that we can automatically identify the bubble and dew point through case study. But I think case study will become an advanced option for you guys because I think starting with this in another workshop we will see that how case study because it will be too much for all of you to understand and digest in a single workshop. So this is all about this workshop where we have to uh, add the composition of the hydrocarbons. There were 4 hydrocarbons we added with a thermodynamic package of Benard Osiron because our operating pressure is less than 100 bar. We go to the simulation, we add the feed composition first, then temperature pressures and flow. Then we add the compressor followed by the cooler to reduce the temperature and we will have the liquid volume vapor ratio in the end with the separator. See, now basis I have changed. It is automatically changing. Mass flows composition. This is the mole fraction I put, but I want to see mass fractions. Mass fraction, it will be automatically calculated. Mole flows, mass flows. So this is also the conversion tools for the graduates that many of the graduated engineers I see uh, rather than doing it with the calculator, they do it with the Hysys like this. They have more confidence on the software rather than the calculations. But in order to run the software like this, you need to have a clear background of the engineering, that how thermodynamic is working, why and where the energy is removing. Because this is a small single flow sheet, but if you see the large models which contain multiple plants, then you need to identify where are your inputs. So if we see few examples from resources, start that because I've already opened one flow sheet. So, but with the software you can add open. If I close this, then I can add open that field.
Shahzeb, I have something to say.
Yes, yes,
Hey, now, you guys, the most important thing here is to interpret the data. As
yes,
Shahzeb
yes,
has, yes, as Shahzeb has indicated to you, whatever you're seeing here, these are operating parameters or conditions. And that's why in our previous sessions, we told you that the heat and mass balance is linked to the process flow diagrams. So what you'll always find on the process flow diagrams are these parameters here, the ones in the table. So Shahzeb has done the simulation, has developed the model. So if you generate this in heat and in Excel, you will get the heat and mass balances, which you can use now to compute or to calculate the size of this separator, the requirements of this heat exchanger for design now. So now what you can observe here, at this temperature here of 58.84, we do not have any liquid flow rate. So that's the dew point. All what is coming in the separator is actually vapor. Is vapor, no liquid flowing out. 0, 0, you can see it here. So you should know how to interpret this. What does that mean? And then Shahzeb, I wanted to suggest, is it possible that we add, assuming we have a vapor, we can change the temperature, we have some liquid flow, and then we are going to store it. Then we include a pump somewhere there. I wanted them to use this data to size that pump, the inlet and the outlet streams, and then size the pump.
I put here 32. Then we have liquid in the bottom stream. What we can do, we can put a pump here, and it will move the liquid at a certain discharge pressure, for example 100 kPa. 100 kPa showing negative temperature means the pressure is very low, and this is the error, yellowish colored error. So I will put 500. Now this is converged. I changed the dynamic color scheme, but default is okay. Now I have the liquid stream at this pressure, and I will employ what we can say the tank, and we will put the tank. We remove, hide the streams, the upper stream like this. So we are now pumping the liquid to the tank. So once you are familiar with the flow sheet and all the requirements, you can add multiple things. For example, you can take one example of any of the process and start simulating it, and you have the numerical results, and once you get the simulation you will have the same results from simulation as well. That will help you to develop a concept, because I remember that in the beginning when I started, what I did, I have the solved problems from the refinery in my notebook. So what I was done at that time, I developed a simulation of it and match the results. Theoretical simulation. And even in the industry, you could not rely totally on the simulation because sometimes if your inputs are not correct, then it will give you a bad result. So you only verify your theoretical results and your assessment based on calculations with the simulation to endorse it completely that your calculations are correct. This is a second hand verification with the simulation. Means you design really well PZV and you have the results. Manually you did this, but you need to verify it because somebody has to verify the calculation. So for the verification purpose, you verify it with the simulation. So you are doing both job. You did the design and you verified the simulation. So nobody can question your credibility and competency that this is correct or incorrect. And you have more confidence that because you did the work and you verified the simulation, you actually endorsed your work. Once you start doing this, you will become and improve in terms of process engineering. So if you have questions now, Benard, regarding the simulation model, and if you are interested in the next workshop, then let me know.
Yes, Shazeb. I just have a addition. So you guys, you can see up there is economics. So if you have the pricing data with you for each stream, you can get the capital for this. Now, if you're estimating the cost, how much you actually need, because here now the major equipment we have, you can see there's a compressor, there's this heat exchanger, there's this separator, pump, and then the storage tank. So if you want to estimate the cost, you can get the price data and you'll be able to estimate the capital here, even the utilities. Yeah, you can see up there. If you have the cost data, even the energy, and then the feasibility, all the risks. You can also even estimate the emissions that you can, that your plant will be emitting. If you are working with an operating plant, you can link to the plant data. You can see up there, plant data. And that is if you want to do it in situ. So maybe what I wanted you to show us is how to get the Excel sheet from this.
The sheet,
Yes.
there are options available. For example, if you click on the Excel, one option is that you click all data here, select all, copy, Control C, Control V, all data pasted in Excel with the streams. And other option could be from the reports. So you create one report, insert data, click all, add,
Is it possible to import all, including the other physical properties that we saw at first, into Excel? They can use that data to size the pump and the lines for them to
the Excel
understand.
directly. The report is generated like this from Aspen, but for Excel, there is another way to do this, but that is from the Excel. there is Aspen simulation workbook. But this is another software. We can do all the things here, but using Excel by enabling it. But let me see another way. Because in the report, it converts into Word file uh, and PDF file. For the Excel, we usually do we usually only copy paste from like this, as I did already. For example, if you want to have the data for the pump,
Yes.
and you go here, Control C, so you will find like this. And for properties, you can also Control C, Control, so all properties will be added like this. Now you can work. It is easy rather than
Yes.
exporting the data from Excel.
Yes. We
Because if
can
I
we
export
can
it, I have to connect it.
we can copy even the flow sheet and paste in Excel, I think.
Yes, this is easy. Because if I connect two softwares together, like Aspen Excel workbook and Aspen Hysys, uh, it will take my more tokens on Aspen Hysys, and also I have to build another sheet in
Okay.
Aspen Excel rather than with the simulation. This will be an additional work. If I know that I have to monitor too many parameters in the Excel, then I will not use the Aspen Hysys. I will start using Aspen Hysys via Aspen Excel workbook. So I will start inputting the data in the Excel directly rather than doing the simulation itself.
Yeah.
So when I click enable, this simulation workbook now open. But this has its own features because if I click here, I have to connect one sheet
Yes. 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 I get you.
and then I will add. Then everything will run on Excel. So Benard, what is now? I hope that all the participants have understand that what we have done in this workshop.
Let's
Um,
call them to ask a few questions if they have or comments. Over to you, guys. If you have a question, if you have a comment, please.
yeah, anything, any experience you want to share? No issue.
Or experience that you want to share.
Your project details, the project you have done during undergraduates, and how you can improve it using simulation by understanding this. Any kind of idea you want to share, then you are most welcome. Yes, Mr. Joy.
I wanted to ask for the simulations, how do you know the packages? That is one, maybe that I'm supposed to pick Peng Robinson, or are these things automatically in the manual, then even the equipment, let me say there are many distillation columns. How do I know that this, or maybe someone already designed it for me? It's just about me creating the simulation.
Yes. Regarding your first question, that how we will select the fluid package, in the Aspen help and also on the internet you will find this table. This is a decision tree called thermodynamic model. So it depends that you need to justify or separate that your components which you are going to use in the simulation is polar or non-polar. Is it all gases or is it liquid hydrocarbon? Means for example it is water or hydrocarbon, gases like methane, ethane, butane, propane. Then if it is all gases and it is hydrocarbon, then the first one you can see, 1, 2 hexagonal, it is showing yes, then we will select Bang Robinson SRK API. If these are electrolytes, means this is Ca plus 2, Na plus 2, NaOH, and like these compounds which have positive negative signs on it, then you can go with these fluid packages. If any gases that have the pressure more than 10 bars, and that is acid gases like ammonia, CO2, and SO2, SO3, then you go to this thermodynamic packages. If the polymers are involved, like polyvinyl chloride, PPA, PDA, polypropylene, like these polymers are involved, then you will go with this fluid packages, SAFT and ESD. If any stream which have the pressure of less than 10 bars, even if it is water, then you can select Henry's law. If no, then you can select if it is more than 10 bars. So if you want to have more detail on this, then you will go in the resources, there is a help available. When you click it, you will write thermodynamic fluid packages. So when you click this fluid packages, you will run something regarding the fluid packages, that how to do it. And if you go here, selecting a suitable fluid package, so you will have the theory available. And we recommend that you use property package selection assistant. So this is the selection assistant for all and processing. You have this, and if I go back, you have refining, you can select this one. If you have chemical, you can select, if the pressure is less than 10 bar, you can select this one. This is a method assistant, selection method assistant. So in
Shazib,
this way you can select.
yes,
Yes, yes.
Shazib, just a quick one. So, guys, what Shazib is telling us is there are two ways. You can use the help icon. Shazib, first go back. You can use the, yes, there. You can use the help icon in Aspen. So depending on the industry you're in or what you're working, if you're working on oil and gas processing, you click there, you'll find there the packages they recommend for you to use. If you're in refining, if you're in chemical, clean fuels, and so forth. So Aspen gives you a guidance on which package you to select depending on which industry. So, or you can use the flow chart as shown us. Then the other thing that Joy was asking, how do you know? Or is there someone who has already created? There are templates. Or you can start from scratch like he did here. He started from scratch. He showed us some templates there when he was starting. Aspen has some templates for different units. You can choose the template and modify, or you can start from scratch. Thank you.
For example, this model is an example developed by Aspen. This is already converged model. I go to the resources and I put examples. Then here I select atmospheric fluid tower. Then it gave me this model, distillation model. And during or initiating the simulation, we should have a clear objective that what is our objective, what we want to do with the simulation. Well, without clear objective, we could not complete the simulation. For example, if you want to see the NAFTA 90%, this is our objective. Then to achieve the NAFTA 90% distillation cut, we need what equipments, what feed quality required, what thermodynamic package. This is watts. How many watts? More question asked to yourself, more clarity you will get. And if and it, and in any way, if you stuck in any question, then you need to ask your supervisor or maybe your mentor that how to deal with it. So this is for doing the simulation. This is me versus me and you versus you. So you want to do the simulation first. I recommend to have a detailed course on it if you don't have any much information about it, because this is just a demo of showing the power of simulation, that how simulation can do different kind of tasks. So this is just was one example, but there are many detailed courses available both in steady state and dynamic state. The one which we did is the steady state, but there is also dynamic state. In the steady state, we put the time constant zero. We steady state we use only for process studies, like on a steady state plant. But for the dynamic, we change the parameter with respect to time. We see the changes in process parameters by changing the timeline. For example, we are depressurizing the tower. So we will see in the dynamic mode that at how many times the tower is depressurized from 10 bar to 1 bar, like this. So in the example mode, we have both available dynamic model also few and compressor cubic curves. Means from basic to advanced level, you will find the example samples. But to understand these samples, you need to have a background, because you need somebody to tell you that why it is used and how it will be used before you expert on this. I think we together give the answer, give the reply to them. First question was regarding the thermodynamic package, how to select it, and second is which equipments we need to select. It depends on our objective. If we are doing distillation modeling, then we will select distillation columns. If we are doing only pump sizing, we will only install pump and so on. So if you guys don't have any further questions, then we can wrap this workshop for today. And I will contact Benard for any future workshop if you guys are interested. Uh, yes, Benard, that's it from my side.
Yes, Shazib, thank you. Do we guys have questions or comments?
Bernard,
Yes. Joseph.
thank you very much. I think Ismail for the presentation. Though I joined late, but I'll ask only one question about the costing or the economics. What is the degree of reliability of the costing output that we can get from this Aspen? Thank you.
Yeah, actually, for the initial estimates, you can use the Aspen cost estimator, but there is another software for Aspen for detailed costing. I think that is the more reliable one. I don't have it currently, but I think that we call capital cost estimator (CCA) for Aspen. This is a different separate product. Uh, for the economics of the large projects, the companies project engineer use that software to identify all the cost. So there are inputs available in that, like uh, the initial piping cost, man labor, and everything. first estimated by the cost estimator, and later it will give you an option to add yours. But in I think the latest version, this version I have is 11.1, but in 11.14.1 there are updated costs region wise. There you can just select the region and the estimated cost you will find. Most of the companies use that capital cost estimator for doing the costing of the project. And for the university projects, people can use this Aspen Assets cost estimation available in it, but that is not the correct one. That is just an estimation.
Thank you, Hassan. Any other comment? Any other question before we close this? As we wait for their comments, I'm going to request you, Hassan, that model we have.
Can you repeat? Your voice interrupt and voice was not clear.
For the
Yes, Benard, I was disconnected. I've joined again.
Okay, Hassan, thank you so much for your time. Thank you for the knowledge and the skill and the experience that you've shared with us. I want to believe that the team here has picked something, has learned. If in case you don't, you have questions or you feared to ask, please, you can still ask. I'll link up with Hassan and then we can get back to you. Otherwise, we really appreciate the time and effort you've given to us. Thank you, Hassan.
Yeah, welcome. And if you have
Okay.
any questions, you can just text me on LinkedIn. Also, you can add me on LinkedIn and even on my YouTube channel, Smart Process Engineering. You can connect me there. You can comment on the videos, and you can personally message me on LinkedIn as well. So if you have
Yes,
any confusion while doing the simulation, then no issue.
before you go off, for those who joined late, this is Hassan's profile. I'm sharing quickly. You can connect with him on LinkedIn and also on YouTube. On YouTube, just go and say Smart Process Engineering. You can link up with him for learning purposes. You can share your experiences, you can discuss. So that's Hassan for today. Thank you, team. Thank you, everyone, for slotting in to participate in today's session. Thank you. Nice weekend, Hassan.
Thank you, everyone. Thank you. See you then. Bye bye.
Bye. Nice weekend, guys.
Nice weekend too.
Thank you.
Thank you, sir.